You know, we're all living at the bottom of a massive ocean of air. And yeah, we notice the big stuff, day and night, the seasons changing. But what if I told you there's another cycle? An enormous, totally invisible tide in the air that washes over the entire planet twice a day. Well, today, we're going to make that unseen force visible.
All right, so let's get this straight. We all know about ocean tides, right? You can see the water level rise and fall. That's mostly the moon's gravity doing its thing. But atmospheric tides, they're a whole different animal. For starters, you can't see them. And their main driver isn't gravity. It's the heat from the sun warming up the air every single day.
And here is the wildest part. This huge, rhythmic wave of air pressure, it's literally passing through you and me right now. It's a planet-sized event, but we have absolutely no sense of it. So the big question we're tackling today is, how on earth can we detect something so massive, yet so incredibly subtle?
To even begin to understand it, we've got to get a clearer picture of what's really going on in this ocean of air that's all around us.
So what are atmospheric tides really? Well, at their heart, they're just predictable, repeating changes in air pressure. You can almost think of it like the atmosphere is breathing on a global scale. But instead of lungs, the whole thing is powered by the daily furnace of the sun. Let's break down how that solar engine actually works. It's pretty straightforward. First, the sun's energy hits our atmosphere. Then, some key molecules, especially water vapor and ozone, soak up that radiation. That absorption heats the air, causing it to expand and create a kind of thermal bulge. And this bulge, this wave of higher pressure, just follows the sun as it moves across the Earth. It's like a giant invisible ripple chasing daylight around the globe.
Now, it turns out not all these tides are created equal. Scientists have a few ways to classify them. You've got migratory tides, the ones we just talked about that follow the sun, but there are also non-migratory tides that are kind of stuck to certain regions, thanks to the influence of continents and oceans. But for what we're doing today, the most important difference is their rhythm. Diurnal tides have one cycle every 24 hours, and semi-diurnal tides have a cycle every 12 hours. Keep those two in mind. They're going to be really important in a minute.
So we know what it is, but how do we prove it's really there? How can we actually listen in on this quiet, atmospheric rhythm? Well, to hear the sky, you first have to build an ear.
And for that, we're going to look at the work of Alberto Villalobos, who set out to do this exact thing. His whole goal, in his own words, was to measure these tiny changes to basically highlight a natural cycle that's happening all around us, but that we just never feel. So we're going to follow in his footsteps.
And what's so cool about this is how simple the setup is. You don't need some huge, fancy government lab. This is basically a backyard observatory. At its core, you've got just two key parts. An Arduino board, that's the brains of the operation, and a barometric pressure sensor. That's our ear, listening for the faintest whispers of pressure change.
The mission itself was pretty straightforward, but you had to be patient. Use this little device to record the atmospheric pressure once every single minute, without stopping, for 5 days in a row. The whole idea was to get enough data to see past the random noise of daily weather and find that rhythm hidden underneath. And after 5 days of non-stop listening, the result was a huge amount of data. Over 7,000 individual pressure readings. Every single one is a tiny snapshot of the atmosphere. And somewhere inside those thousands of numbers was the signal we were hunting for.
Okay, now for the really fun part. Digging through all that data to find the atmosphere's hidden heartbeat.
So when you first plot all 7,000 of those data points, honestly, it just looks like a mess. It's noisy, you can kind of see it going up and down, but it's all jagged and looks totally random. It's just all the little fluctuations from local weather passing by. The signal of the tide is buried deep in there, somewhere. So this is the million-dollar question, right? How do you pull a faint rhythmic signal out of all that chaotic noise? Can we actually find a clear repeating pattern in this mess?
And the answer is a definite yes, thanks to a cool mathematical tool called a periodogram. It's basically a filter that sifts through data looking for any repeating cycles. And when you run our data through it, the results are just crystal clear. The analysis found a main, dominant cycle repeating every 11.9 hours. That's our semi-diurnal tide. And right on its heels, a secondary cycle at almost exactly 24 hours, the diurnal tide. They were in there the whole time.
Once you pull out that main 12-hour cycle, you can see the atmosphere's daily pulse with incredible clarity. The pressure consistently bottoms out around 3 a.m., climbs to a peak around 9 a.m., drops back down to a minimum around 3 p.m., and then peaks again around 9 p.m. It's like clockwork, twice a day, every single day.
So just how big is this pressure wave we're talking about? Well, the entire change is only about plus or minus 2.5 millibars. That is such a tiny, tiny change in pressure. It's no wonder we can't feel it. But it is absolutely there, a constant planetary scale rhythm.
Okay, so we found it, we measured it. But so what? Does this tiny hidden wave actually matter in the real world? Oh yeah, the answer is a big yes.
Even though it's subtle, this atmospheric tide has some huge effects. It acts like a global regulator, helping to shape large-scale wind patterns and how temperature gets spread around the planet. It actually influences the stability of our climate. And, this is really cool, it might even have an effect on the animal kingdom, providing faint pressure clues that help guide migratory birds and insects on their amazing journeys.
And I think that's the most amazing takeaway from all of this. We started with just a simple sensor in a room, collecting one data point every minute. And by looking at that data, we were able to see a fundamental force of nature, a subtle, invisible tide that's playing a part in shaping the climate of our entire world. This whole journey, from a simple question to a huge planetary insight, it just shows why looking for these hidden patterns is so incredibly important.
And that kind of leaves us with one last, really exciting question. We've uncovered the atmosphere's heartbeat, but what other invisible rhythms are pulsing all around us, in the air, in the ground, in the oceans, just waiting for a curious person and the right sensor to bring them into the light?